We are going to continue the discussion on problem 1 from 2018 at the Canadian Mathematical Olympiad. Okay, so there was a part 1 video on this problem, and you can find the description of the problem in that video. Just a quick summary. So basically we start off with some tokens in the plane. Here's a particular case where we have T1, T2, T3, 3 tokens in the plane, and we have this collapsing process where we pick 2 tokens and we move them at the midpoint of the segment determined by the 2 tokens. So for example, this original setup of ours will become this, okay, if we choose to collapse the tokens T1 and T2. And we continue to do so for finitely many steps. So the problem is saying, show that any family of n tokens is collapsible if and only if n is a power of 2. Okay, and in that previous video we actually showed this implication. So we showed that if n is a power of 2, then any family of n tokens is collapsible. We are now going to show this other implication. Okay, and here's how we are going to do it. So think about it. We've got this process of collapsing tokens. Okay, again, geometry, it's easy to see. Maybe it's hard to put in formulas, but this is why we associate a system of coordinates. So we said, okay, here's a family of n tokens. Okay, token T1 with coordinates x1, y1, token T2 with coordinates x2, y2, and so on and so forth. All right. Now, if we choose to collapse tokens T1 and T2, okay, we get this other family of tokens. All right. So as you notice, token T3 is unchanged, and all the tokens from T3 to Tn stay the same. Okay, it's just that tokens T1 and T2 will change their coordinates. Okay, and this is the common coordinate of the tokens T1 and T2. So now I'm thinking, well, we can collapse various tokens, so we have a lot of freedom into what we do and what we collapse. Do we actually understand any relationship? Okay, so do we understand any relationship at all? Okay, in between one arrangement of these tokens and the arrangement that we get after we collapse. Because if we do not understand any relationship, how are we going to supposed to be able to say if the original arrangement is collapsible? Okay, so maybe pause the video for a minute and think about that question. All right. Now, the relationship that I see in between this particular arrangement of tokens and this particular arrangement of tokens is the following. Let's say if G1 is the center of gravity of this particular arrangement of tokens, so G1 is the point that we obtain by averaging the coordinates of these tokens. Okay, so G1 here will have coordinates x1 plus x2 plus xn over n, and y1 plus y2 plus yn over n. Okay, so if this is the center of gravity of this particular arrangement of tokens, and G2 is actually this, the center of gravity of this arrangement of tokens, after a little bit of algebra, we can tell that G2 will also have the coordinates x1 plus x2 plus xn over n, and y1 plus y2 plus yn over n. All right, so actually the two are the same. Okay, so we picked two random tokens, we collapsed them, but what stays the same is the center of gravity of the two arrangements. So now we got our invariant. All right, so the center of gravity stays the same no matter what tokens we choose to collapse. Well, now I believe this is power in our hands. Okay, because if the set of tokens is collapsible, we know where it will collapse, and it will collapse right here. Okay, because that the final setup of tokens will have all tokens on the same position, and that's the position. All right, now how is this helpful towards us solving the problem? Well, how about we take a look at a specific family of tokens. So let's say this is the system of coordinates, and we take here at the origin of the system of coordinates, we take here the tokens t1, t2 up to tn minus 1, and let's say here, which is this is the point of coordinates 1 and 0, we take the token tn. Okay, so we look at a specific family of n tokens, because what we want to prove is that any family is collapsible if n is of power 2 to the power of k. All right, so now, okay, how are we going to collapse these tokens? Well, because all of them are collapsed with the exception of this one here, the only way to change this family is by taking one of these tokens from here and this token from here, right? So we are going to move them at the midpoint of the segment determined by these 2 points here. So basically now we are going to have a bunch of tokens at 0. Well, again, how about we come up with an extra simplification of this problem, just because of the fact that these tokens are already on the x-axis. Okay, when we actually move them, they will stay on the x-axis. So let's ignore the y-axis for now. Okay, so basically we've got some tokens on 0 on this axis and at 1 on the axis, right? And then what we do is we take one of the tokens from here and this token here, and we move them at 1 over 2. Okay, so now so these were the x-coordinates that we got up to this point. Now what we are going to do, okay, so remember we have a bunch of tokens left here and we have 2 tokens here. The only way to make progress into arranging these tokens is by moving them halfway through. So we are going to get a token at 0.1 over 4 on the x-axis. Okay, so now what are we going to do? Well, so we take again one of these tokens and from one position and another one from another position. All right, so we can see that, for example, if we take one token from 0.1 over 2 and one token from 0.1 over 4, we get a token, or 2 tokens actually, at coordinates 3 over 8. Okay, so we already see a pattern here that the idea is that no matter how we do things in this particular setup, okay, we are going to get tokens at a coordinate, okay, whose numerator, not necessarily that I have control over, but the denominator of it is going to be a power of 2. All right, so no matter how we pick tokens in this particular family, the denominator of the new position of tokens is going to be a power of 2. Now, but what's the center of gravity of this original family? Well, we have all the tokens but one at 0 and one token at 1 and 0. So the center of gravity will end up at the point 1 over n and 0. Well, so now it becomes clear that in order for this family, for this particular family to be collapsible, it's got to be the case that n has to be a power of 2. Okay, so now we saw how us figuring out an invariant of this algorithm allowed us to figure out that this particular family of n tokens is collapsible if and only if n is a power of 2. And that concludes our proof.